Picture a time when the universe was nothing but a swirling, chaotic sea of energy, mere moments after the Big Bang. No stars, no planets, not even atoms as we know them today. But hidden within that chaos were the very first molecules, tiny building blocks that would one day shape everything we see around us. These primordial molecules are like cosmic fingerprints, holding secrets about how our universe evolved from pure energy to the vast, structured cosmos we know now. What were these first molecules, and how did they set the stage for everything that followed? That's the mystery we're about to unravel. Think about the air you breathe, the water you drink, even the screen you're staring at right now. Every bit of matter in your life traces its lineage back to those earliest molecules. They were the pioneers, the first to form in a universe still too hot and violent for anything stable to exist, and yet, against all odds, they emerged. Scientists believe these molecules weren't just random accidents. They were the universe's first steps toward complexity, the silent architects of cosmic order. So what does that mean for us? Understanding them isn't just about peering into the past, it's about discovering the very rules that allowed life to exist at all. Here's the wild part: we're still uncovering their secrets. Cutting-edge telescopes and advanced simulations are letting us catch glimpses of these ancient molecules, like detectives piecing together a billion-year-old crime scene. Some of these discoveries challenge everything we thought we knew about chemistry and space, while others hint at even deeper mysteries waiting to be solved. That's why this journey isn't just for scientists, it's for anyone who's ever looked up at the night sky and wondered how it all began. So buckle up, because we're about to dive into the origins of existence itself, exploring 30 mind-blowing theories about the universe's first molecules and what they reveal about our place in the cosmos. The story starts now. Right after the Big Bang, the universe was like a cosmic chemistry lab running at unimaginable temperatures, so hot that even atoms couldn't hold together. For the first few 100,000 years, space was just a fog of charged particles, a swirling plasma too energetic for electrons to settle around nuclei. But as the universe stretched and cooled, something extraordinary happened. Hydrogen and helium, the lightest and simplest elements, finally emerged as the very first stable molecules in existence. Picture this: a vast, dark ocean where these two gases were the only ingredients, the primordial soup that set the stage for everything to come. Hydrogen dominated the scene. It was the universe's first building block, making up nearly 3/4 of all normal matter. Helium followed close behind, accounting for almost everything else. But here's the catch: nothing heavier existed yet. No carbon for life, no oxygen for water, no silicon for planets. Just these two lightweight players in an otherwise empty cosmic kitchen. And yet, this simplicity was crucial. Hydrogen and helium's stability allowed them to survive the violent conditions of the early universe, forming the first molecular bonds in the cold pockets of space as temperatures dropped further. Scientists call this era the Dark Ages because without stars or heavier elements, the universe was literally invisible, no light beyond the fading glow of the Big Bang itself. But within that darkness, hydrogen and helium quietly laid the groundwork for cosmic evolution. Gravity began pulling these gases together, creating dense clouds that would eventually ignite as the first stars. Those stars, in turn, would forge the heavier elements in their cores, seeding the universe with the materials for planets, oceans, and even life. So while hydrogen and helium might seem basic today, they were the universe's original alchemists, transforming chaos into structure one molecule at a time. What's fascinating is how much we can still learn from them. The ratios of hydrogen to helium in today's universe match predictions made by Big Bang theory, serving as a smoking gun for how matter first organized itself. And in distant, ancient gas clouds, astronomers have detected traces of these primordial molecules, preserved like fossils from the dawn of time. They're not just relics, they're proof of how even the simplest ingredients can, given billions of years and the right conditions, build something as complex as a galaxy or us. But while hydrogen atoms floated freely in that ancient darkness, something remarkable was happening in the shadows. Without stars to illuminate the cosmos or complex elements to interfere, these lone hydrogen atoms began an intricate dance, slowly pairing up to form the universe's very first molecular bonds. This wasn't just random chemistry, it was a delicate balancing act. The early universe was still cooling, and as temperatures dropped, single hydrogen atoms could finally latch onto one another, creating fragile H2 molecules, the simplest possible union of matter in existence. Here's where things get counterintuitive. These molecules didn't form the way they do today. Normally, hydrogen needs a surface to cling to, like a speck of dust, to help atoms stick together. But in that pristine era, dust didn't exist yet. So how did H2 emerge? Scientists believe dark matter played a hidden role. Though invisible and mysterious, its gravitational pull carved out slight density variations in the primordial gas. These subtle wrinkles created cold pockets where hydrogen atoms could lose energy just enough to bond, like two exhausted dancers finally catching each other in the dark. The implications are staggering. Those first H2 molecules acted as cosmic refrigerators, helping gas clouds cool even further by radiating away heat. This cooling effect allowed gravity to work more efficiently, compressing the gas into denser clumps that would eventually collapse into the first stars. Without molecular hydrogen, the universe might have remained a formless haze forever. Even more intriguing, the fingerprints of this process might still be detectable. In distant, undisturbed corners of space, astronomers have spotted clouds of H2 so ancient they've barely changed since the Dark Ages, time capsules preserving the chemistry that kick-started cosmic evolution. But dark matter's role goes deeper. Simulations suggest its invisible scaffolding guided where and how those first molecules formed, shaping the distribution of gas that would later birth galaxies. Think of it like an unseen architect quietly arranging the framework for everything visible to emerge. This interplay between dark matter and H2 reveals a universe where even the most ethereal forces had a hand in building the tangible cosmos we know today. So while we can't see dark matter directly, its influence is written into the very molecules that made stars and ultimately us possible. Now imagine floating through space in those early times, not just through empty blackness, but through vast clouds of gas so thin they'd make Earth's atmosphere seem solid by comparison. Yet within those clouds, something tiny but mighty was at work: cosmic dust. These microscopic particles, no larger than a grain of fine sand, became the unsung heroes of molecule creation. Without them, hydrogen and helium might have remained solitary wanderers forever, but dust changed everything. Each speck acted like a minuscule chemistry lab, offering a surface where atoms could cling and meet. Picture it like a cosmic dance floor: hydrogen and helium atoms, bouncing around chaotically in space, suddenly finding a place to land. When they stuck to a dust grain, they lost energy, slowing down just enough to bond. This wasn't just a chance encounter, it was the universe's first recipe for complexity. Dust didn't just help form simple hydrogen molecules, it set the stage for more elaborate chemistry, like helium hydride, the first molecular compound ever detected in space. Here's where things get even more fascinating. These dust grains weren't just passive platforms. They absorbed the faint heat of the early universe, radiating it away and creating cold spots in the gas clouds. That cooling effect was like turning down the thermostat in a boiling room, allowing more atoms to settle and bond. Over millions of years, this slow, silent process transformed diffuse gas into denser patches, the nurseries where future stars would be born. Without dust, the universe might have remained too hot and turbulent for structure to emerge. But where did this dust even come from? In a universe still devoid of stars or planets, its origins are a puzzle. Some theories suggest it formed in the violent aftermath of the Big Bang, as exotic particles clumped together in the cooling chaos. Others propose it was forged in the hearts of the first supernova explosions, ejected into space as dying stars scattered their guts across the cosmos. Either way, this dust was more than debris. It was the universe's first infrastructure, a scaffold for building everything that followed. Today, astronomers study these ancient dust grains like forensic scientists examining a crime scene. By analyzing the light absorbed by distant gas clouds, they've found signatures of molecules clinging to dust billions of years ago. These observations match laboratory experiments where scientists recreate space conditions, watching hydrogen and helium bond on synthetic dust in vacuum chambers. It's a rare case where cosmic history can be tested right here on Earth, and the findings are clear. The humble dust grain was the quiet architect of cosmic chemistry, turning the simplicity of the early universe into the rich molecular tapestry we see today. This raises a mind-bending possibility. If dust was essential for building the first molecules, could it also hold clues about how life's ingredients eventually formed? Some of the complex organic molecules found in modern space, dust like water, ammonia, or even amino acids, might trace their lineage back to these primordial processes. In that sense, the dust under your bookshelf isn't so different from the stardust that once seeded the cosmos. It's all part of the same grand story, where the tiniest particles helped create the largest structures in existence. Among the swirling hydrogen and helium of the early universe, there was a whisper of something else, a trace element that might have played a far bigger role than its scarcity suggests. Lithium, the third lightest element, existed in vanishingly small amounts after the Big Bang, outnumbered by hydrogen 1,000,000,000 to 1. Yet this underdog of the periodic table could have been part of one of the universe's first true chemical compounds, lithium hydride. Picture this: while hydrogen molecules were busy pairing up, a few lucky lithium atoms managed to grab hold of hydrogen partners, forming bonds in the cosmic chaos. These fragile Li-H molecules wouldn't have lasted long, but their fleeting existence could have left fingerprints we're only now learning to read. Why does this matter? Lithium hydride isn't just another molecule, it's a cosmic stepping stone. Unlike simple hydrogen gas, Li-H carries an electric dipole moment, meaning it can absorb and emit radiation far more efficiently. In a universe still cooling from the Big Bang, that ability would have been game-changing. Imagine these molecules as microscopic sponges, soaking up stray photons and helping to bleed heat from the primordial gas clouds. That extra cooling could have accelerated the collapse of matter into the first stars, subtly altering the timeline of cosmic evolution. The evidence is tantalizing but elusive. Astronomers hunting for lithium hydride face a needle in a haystack challenge. Even if it formed, most of it would have been destroyed by the intense ultraviolet light of the first stars. But here's the twist: we might have already detected its ghost. In 2018, scientists studying the atmosphere of a distant brown dwarf spotted the chemical signature of Li-H, the first confirmed detection outside a lab. This failed star, too cool to burn hydrogen, mirrors the cold conditions of the early universe, offering a snapshot of how these molecules could have behaved billions of years ago. The real surprise: lithium hydride might have shaped the cosmic microwave background, the faint afterglow of the Big Bang itself. Theoretical models suggest Li-H molecules could have scattered photons in specific patterns, leaving faint imprints in this primordial light. If future telescopes can decode those patterns, we might finally prove that this humble compound was there at the dawn of chemistry, quietly helping to sculpt the universe into what it is today. So while lithium hydride never had the abundance of hydrogen or the staying power of helium, its brief spotlight on the cosmic stage could have been one of the most influential performances in history. Deep in the primordial soup of the early universe, there was a rare but critical player, deuterium, hydrogen's heavier cousin. While regular hydrogen atoms contain just one proton and one electron, deuterium packs an extra neutron in its nucleus, making it slightly denser and far more elusive. This tiny difference might seem insignificant, but in the delicate chemistry of the early cosmos, it changed everything. Picture a universe where for every million hydrogen atoms, only a few dozen deuterium atoms existed. Yet these rare heavyweights could have been the key to unlocking molecular complexity long before stars lit up the darkness. The mystery begins with their formation. In the furious first minutes after the Big Bang, as protons and neutrons whirled in a sea of energy, deuterium nuclei briefly flickered into existence only to be torn apart again by the intense heat. It wasn't until the universe cooled enough, roughly 3 minutes after creation, that deuterium could finally stabilize. This narrow window left behind just a trace amount, like cosmic breadcrumbs for scientists to follow. But here's the puzzle. The deuterium we observe today doesn't quite match theoretical predictions. Some of it seems to have vanished, and the best clues to its fate lie in the cosmic microwave background, the faint afterglow of the Big Bang itself. That's where things get fascinating. Deuterium's extra neutron gave it unique chemical superpowers. When it bonded with hydrogen, forming heavy hydrogen molecules like HD hydrogen deuteride, these compounds radiated heat far more efficiently than ordinary hydrogen pairs. In the cold pockets of the early universe, that extra cooling could have turbocharged the collapse of gas clouds, accelerating the birth of the first stars. Think of it like adding ice cubes to a simmering pot. The temperature drops faster, changing how everything cooks, but deuterium's story doesn't end there. Recent studies of ancient gas clouds, observed through the light of distant quasars, reveal deuterium clinging stubbornly to space dust billions of years later. These cosmic relics suggest deuterium wasn't just a passive ingredient, it might have been a catalyst, fostering the formation of more complex molecules by acting as a bridge between hydrogen and other elements. Laboratory experiments back this up. When scientists recreate early universe conditions, deuterium-containing molecules form at lower temperatures and stick together more tightly than their hydrogen-only counterparts. The real shocker, deuterium could hold clues to one of cosmology's biggest headaches, the missing baryon problem. Observations suggest about a third of the universe's normal matter is unaccounted for, and deuterium's delicate abundance is like a cosmic scale, sensitive to how much ordinary matter existed in those first moments. By mapping deuterium concentrations in different regions of space, astronomers are piecing together where that missing matter might be hiding, perhaps locked in vast, invisible filaments of warm gas stretching between galaxies. So next time you hear about heavy water or nuclear fusion, remember, deuterium isn't just a scientific curiosity. It's a time capsule from the universe's first chemistry set, a relic that shaped cosmic evolution in ways we're only beginning to grasp. And as new telescopes peer deeper into space and further back in time, we might finally solve the riddle of how this rare, heavy hydrogen helped turn a featureless cosmos into a universe brimming with stars, planets, and life. Among the sparse, scattered gases of the early universe, certain regions began to thicken like swirls of cream in cosmic coffee, dense pockets where hydrogen, helium, and dust grains clustered tighter than anywhere else. These weren't just random clumps, they were the universe's first molecular clouds, colossal nurseries where chemistry and gravity teamed up to build the foundations of everything we know today. Picture these clouds as vast, shadowy wombs, cold enough for atoms to slow down and stick together, yet turbulent enough to churn out the first complex molecules. Inside their depths, simple hydrogen pairs evolved into elaborate chains, while dust grains acted like microscopic factories, welding atoms into new configurations never before seen in the cosmos. What made these clouds so special? For starters, their sheer size defies imagination. A single molecular cloud could stretch hundreds of light years across, containing enough material to birth thousands of stars. But their true power lay in their cold, dark hearts. Shielded from external radiation by layers of gas and dust, temperatures in these regions plunged close to absolute zero, creating the perfect conditions for molecules to form and survive. Here, hydrogen didn't just pair up, it danced with carbon, oxygen, and nitrogen, crafting compounds like carbon monoxide and water ice. These molecules weren't just passive residents, they were cosmic coolants radiating away heat and helping the cloud contract even further. It's like the cloud was building its own scaffolding, molecule by molecule, to collapse into something greater. The process wasn't smooth or steady. Turbulence ripped through these clouds, stirring the gas into filaments and knots. In some spots, gravity gained the upper hand, pulling material into dense cores so compact that not even light could escape. These were the seeds of the first stars, and the molecules within them became the raw fuel for stellar furnaces. But before ignition, another marvel unfolded: chemistry. On the surfaces of dust grains, atoms assembled into prebiotic molecules like formaldehyde and methanol compounds that would later become the building blocks of life. It's almost poetic. The same clouds that birthed stars also sowed the ingredients for biology, all while the universe was still in its infancy. Modern astronomy lets us peer back into these ancient nurseries. Telescopes like ALMA detect the faint radio whispers of molecules in distant galaxies, revealing chemical recipes frozen in time, one stunning discovery. Even in the earliest clouds, organic molecules existed in abundance, proof that the universe was experimenting with life's ingredients long before Earth existed. And here's the kicker: some of these primordial clouds never fully collapsed. They linger today, drifting between stars as cosmic time capsules, their chemistry unchanged for billions of years. Studying them is like cracking open a textbook from the universe's first chemistry class, with lessons written in the language of molecules. This leads to a breathtaking realization: the gas in your lungs, the water in your glass, even the carbon in your DNA, all of it was forged in clouds like these. Every atom heavier than hydrogen and helium was either cooked inside a star or assembled in the molecular nurseries that preceded them. So when you look up at the night sky, you're not just seeing stars, you're gazing at the descendants of those first chaotic, creative clouds. They didn't just set the stage for star formation, they wrote the opening act of our cosmic story. For molecules to survive in the early universe, they faced an invisible gauntlet of destruction, relentless ultraviolet radiation so intense it could rip atoms apart with ease. This was the ionization barrier, a brutal period when photons packed enough punch to strip electrons from their orbits, leaving behind a sea of charged particles too unstable to form molecular bonds. Imagine trying to build a house of cards in a hurricane. That was the challenge facing the first fragile hydrogen and helium molecules. The universe wasn't just hostile to complexity, it was actively dismantling it faster than chemistry could assemble it. The culprit, a cosmic catch-22. The same stars that would later seed the universe with heavier elements began their lives as voracious radiation factories, flooding space with high-energy photons. Before these stars even ignited, the residual heat from the Big Bang kept temperatures high enough to prevent widespread cooling, meaning molecules could only form in rare, shadowy pockets where radiation couldn't reach. These molecular safe havens were like dimly lit back alleys in a brightly lit city, the only places where atoms could huddle together undisturbed, but nature found workarounds. In the densest regions of gas clouds, hydrogen atoms acted as tiny radiation shields. When a high-energy photon hit one atom, others nearby absorbed the shock wave, protecting deeper layers where molecules could quietly take shape. Over millions of years, this natural filtering allowed molecular hydrogen to accumulate, creating cooler, darker cores increasingly resistant to disruption. It's a cosmic version of crowd surfing, each atom absorbing a bit of the blow so others could survive intact. Here's where things get counterintuitive. That same deadly radiation may have actually helped chemistry in the long run. When photons smashed apart molecules, they didn't just destroy, they created reactive fragments like ionized hydrogen H+ and free electrons. These charged particles became molecular matchmakers, colliding with neutral atoms and lowering the energy needed for new bonds to form. Laboratory experiments show that ionized environments can accelerate certain chemical reactions by a factor of 1,000. So while radiation was the barrier, it also held the key to overcoming it. Modern telescopes reveal echoes of this epoch. In distant quasars, the brilliant cores of ancient galaxies, astronomers detect absorption lines that tell a story of molecules forming and being torn apart in cycles. The data suggests that even in the harshest environments, molecules found ways to persist, adapting to the radiation rather than surrendering to it. This resilience hints at a deeper truth. The universe's first chemistry wasn't just about creation. It was about endurance, a testament to how even the most fragile structures can outlast the fiercest storms. In the deep freeze of the early universe, where temperatures hovered just a few degrees above absolute zero, atoms should have been too sluggish to overcome the energy barriers required for chemical bonding. Classical physics says those first hydrogen molecules never stood a chance, yet somehow they formed anyway. The answer lies in one of the most bizarre yet fundamental quirks of nature: quantum tunneling. Picture an atom not as a solid billiard ball, but as a fuzzy cloud of probabilities, with a chance to suddenly appear on the other side of an energy barrier as if by magic. This wasn't just chemistry, it was chemistry with a quantum cheat code. Here's how it worked. When two hydrogen atoms drifted near each other in the primordial darkness, their electron clouds created a tiny energy hill, a repulsive force that should have kept them apart. Under normal conditions, they'd need a violent collision or extreme heat to surmount that barrier. But in the quantum realm, particles don't always play by those rules. There was always a slim chance, governed by the uncertainty principle, that an atom's position could tunnel through that barrier spontaneously. It's like rolling a marble toward a mountain and watching it vanish from one side only to reappear on the other without ever climbing the slope. In the near-perfect vacuum of space, where atoms might wait millions of years between collisions, that tiny probability became their saving grace. The implications are staggering. Without quantum tunneling, molecular hydrogen, the universe's first stepping stone to complexity, might never have formed in significant quantities. Early gas clouds would have remained too hot and diffuse, delaying star formation and altering the entire cosmic timeline. But tunneling didn't just enable bonding, it turbocharged it. Laboratory experiments recreating early universe conditions show hydrogen molecules forming 10,000 times faster than classical physics predicts, all thanks to this quantum shortcut. What's even wilder, this process left fingerprints we can still detect. The coldest molecular clouds in today's universe, where temperatures mimic those ancient conditions, exhibit bonding rates that only make sense when quantum effects are factored in. Astronomers have even spotted peculiar infrared signatures in distant galaxies, ghostly echoes of hydrogen molecules that shouldn't exist unless tunneling gave them a head start. Perhaps the most mind-bending realization is that quantum tunneling didn't just assist early chemistry, it shaped its very direction. Heavier molecules like helium hydride, though rare, formed more readily because their lighter components could tunnel more efficiently. This subtle bias might have set the stage for why certain molecular pathways dominated over others, steering the universe toward the chemistry that eventually made life possible. So the next time you marvel at the stars, remember, their existence owes as much to the subatomic sleight of hand happening in the darkness as to the nuclear fires burning within them. The universe didn't just stumble into complexity, it tunneled through the impossible. Among the sparse chemical offerings of the early universe, methane stands out as a tantalizing possibility, a simple yet profound molecule that might have been the first organic compound to form in the cosmos. Imagine a time before stars forged complex elements, when hydrogen dominated the scene. In this hydrogen-rich environment, the chance encounter of a single carbon atom with 4 hydrogen partners could have created methane, a molecule we now associate with swamps and natural gas, but one that may have played a far grander role in cosmic history. The debate hinges on carbon scarcity in the early universe. After hydrogen and helium, carbon was the next most likely element to emerge from the Big Bang, but in trace amounts, perhaps just 1 carbon atom for every 10 million hydrogen atoms. Yet, given the vastness of space, even those odds meant methane could form in isolated pockets where carbon atoms wandered into the right chemical conditions. Some models suggest that in the coldest reaches of primordial gas clouds, where temperatures dipped near absolute zero, carbon could have snatched up hydrogen atoms one by one, assembling methane like a microscopic Lego structure in the dark. What makes this idea controversial isn't just the question of whether methane existed, it's whether it could have survived. The same ultraviolet radiation that threatened other early molecules would have attacked methane mercilessly, breaking its bonds apart. But here's where the plot thickens. Methane might have had protectors. Dust grains, those cosmic chemistry platforms, could have shielded methane molecules on their surfaces or even catalyzed their formation. Laboratory experiments show that when carbon and hydrogen are deposited on icy dust analogues under space-like conditions, methane forms readily and sticks around far longer than it would in open space. If methane did persist, its implications are staggering. As the simplest organic molecule, it represents the first rung on the ladder toward probiotic chemistry, the steps that eventually lead to life. Methane's tetrahedral structure makes it remarkably stable, yet flexible enough to participate in further reactions. In modern astrobiology, methane is considered a key ingredient in the synthesis of more complex organics, like amino acids or sugars. If it existed early on, even in tiny amounts, it could have seeded the universe with the building blocks of biochemistry long before planets provided hospitable environments. The evidence for primordial methane remains elusive but not absent. Astronomers have detected methane in some of the oldest known gas clouds, dating back to when the universe was just a few % of its current age. These molecules shouldn't have survived billions of years unless they formed continuously, perhaps in shielded environments or through alternative pathways we haven't yet uncovered. Even more intriguing are the methane ices found in comets and interstellar dust, which some scientists argue could be relics of those earliest chemical processes. Ultimately, the methane question isn't just about one molecule, it's about rewriting the timeline of cosmic chemistry. If organic molecules like methane existed before the first stars, then the universe was experimenting with life's ingredients far earlier than we thought. That doesn't just change our understanding of the past, it raises profound questions about how common, or how rare, the path to life might truly be across the cosmos. Helium hydride sounds like a molecule straight out of a chemist's daydream, a fragile bond between the universe's most stubborn noble gas and its lightest element. Yet this improbable pairing, He+, might hold the title of the very first molecular bond in existence. The story of its detection reads like a cosmic detective novel, complete with false leads, decades of searching, and a final breakthrough that rewrote chemistry's origin story. In 2019, astronomers pointed the Stratospheric Observatory for Infrared Astronomy, or SOFIA, toward a planetary nebula called NGC 7027, 3,000 light-years away. Nestled in the glowing wreckage of a dying star, they found the long-sought fingerprint of helium hydride, a discovery that should have settled a century-old debate. But in science, even landmark findings come with asterisks. The controversy begins with helium itself. As a noble gas, it's notorious for resisting chemical bonds under normal conditions. Yet in the early universe's extreme environment where temperatures soared and particles crashed together with unimaginable force, helium's aloof nature broke down. When a helium atom lost an electron to ultraviolet radiation, it became positively charged, transforming into a desperate atomic matchmaker. This ionized helium, He+, could grab hold of a passing hydrogen atom, forming He H+ in violent, short-lived unions. Theoretical models predicted this molecule would dominate chemistry in the universe's first 100,000 years, paving the way for more stable hydrogen molecules to form later. But proving it existed required finding its spectral signature, a faint infrared glow at a specific wavelength. That's where the plot twists. Previous attempts to spot He H+ in space kept hitting dead ends. Earth's atmosphere blocks the key infrared frequency, making ground-based telescopes useless. Early claims of detection in the late 1990s near a star called IRC plus 1020 were later disputed when other teams couldn't replicate the results. Even SOFIA detection faced skepticism. Some researchers argued the signal could be confused with other molecular emissions or instrumental noise. The nebula's modern environment, rich in heavier elements, also raised questions. Was this truly a relic of primordial chemistry, or just a late-stage byproduct of stellar death? The answer might lie in quantum mechanics. Helium hydride's bond is bizarrely delicate, relying on a phenomenon called charge polarization. The hydrogen atom, though neutral, gets distorted by the positively charged helium, creating a lopsided electron dance that barely holds the molecule together. In lab experiments, He H+ survives only in near-perfect vacuums at temperatures near absolute zero, conditions eerily similar to the early universe's cold, sparse pockets. This fragility made it the perfect pioneer molecule, abundant enough to kickstart chemistry, yet unstable enough to disappear once more robust bonds took over. What's at stake isn't just a technical footnote. If helium hydride was indeed the first molecular bond, it reshapes our understanding of cosmic evolution. Before stars forged heavier elements, before dust grains offered reaction surfaces, He H+ could have been the universe's sole molecular bridge between atoms, a fleeting but essential step from simplicity to complexity. Its detection also validates decades of quantum chemistry models, proving that even the most exotic theoretical bonds can manifest in reality, yet the debate isn't closed. New telescopes like the James Webb Space Telescope could search for helium hydride in even earlier cosmic epochs, where uncontaminated primordial gas might preserve its original abundance. Until then, this molecule remains both a triumph and a tantalizing mystery, a ghost from the universe's first chemical whispers, still daring us to listen closer. Before stars filled the cosmos, the universe was a molecular desert, just hydrogen, helium, and traces of lithium drifting through an endless void. Then came population Roman 3, the first generation of stars, and everything changed. These celestial titans, forged from pure primordial gas, burned hotter, brighter, and died more violently than any star that followed. Their cataclysmic deaths didn't just light up the cosmos, they reprogrammed its chemistry. When these metal-free giants exploded as supernova, they didn't just release energy, they unleashed the first heavy elements into the universe, transforming it from a place of simplicity to one of staggering complexity. What made population Roman 3 stars so different? Imagine a star with no impurities, no carbon, no oxygen, no iron, just pristine hydrogen and helium fused under crushing gravity. Without heavier elements to help cool the gas clouds that birthed them, these stars grew to colossal sizes, some weighing over 100 times more than our Sun. Their sheer mass dictated their fate. They lived fast, burning through their fuel in mere millions of years before detonating in supernova so powerful they could outshine entire galaxies. In their final moments, they became cosmic alchemists, forging elements like carbon, oxygen, and silicon in their cores, ingredients that had never existed before. The aftermath was a chemical revolution. Each supernova scattered these newly minted elements across space, seeding the cosmos with the raw materials for molecule formation. But here's where things get surprising. These explosions didn't just distribute atoms, they created environments ripe for molecular chemistry. The shock waves from supernova compressed surrounding gas, triggering reactions that formed molecules like carbon monoxide and water in the debris. These weren't gentle processes, they were cosmic pressure cookers with temperatures and densities so extreme they forced atoms together in ways that would have been impossible in the quieter early universe. Yet population Roman 3 stars left another, darker legacy. Some theorists suggest their supernova produced so much ultraviolet radiation that they sterilized vast regions of space, breaking apart fragile molecules before they could stabilize. It's a paradox. The same stars that enriched the cosmos also made parts of it temporarily more hostile to chemistry. But over millions of years, the balance shifted. As these heavy elements mixed with cooler gas clouds, they acted like cosmic refrigerants, radiating heat away more efficiently than hydrogen ever could. This cooling effect allowed denser, more complex structures to form, including the next generation of stars and eventually planets. The ghostly fingerprints of population Roman 3 stars might still be detectable today. In the atmospheres of the oldest known stars in our galaxy, astronomers have found minuscule traces of elements like iron and carbon elements that could only have come from those first supernovae. Even more telling are distant quasars whose light passes through ancient gas clouds, revealing absorption lines that match the unique chemistry expected from population Roman 3 remnants. These cosmic breadcrumbs hint at a time when the universe was still learning how to build complexity, one supernova at a time. Perhaps the most profound realization is this: every molecule in your body that isn't hydrogen or helium, the oxygen in your lungs, the iron in your blood, was forged in the heart of a star that died billions of years ago. Population Roman 3 stars were the universe's first chemists, turning the simplicity of the Big Bang into the diversity we take for granted today. Without their explosive creativity, the molecular richness that made life possible might never have existed. So when you look up at the night sky, you're not just seeing stars. You're seeing the aftermath of a revolution that began with the first generation of cosmic pioneers. Just as the universe's first molecules began establishing a fragile foothold in the darkness, an apocalypse of light rewrote the rules. Cosmic reionization, the epoch when the first stars and galaxies flooded space with ultraviolet radiation, didn't just illuminate the cosmos, it scorched it clean. Picture a cosmic tsunami of high-energy photons crashing through those delicate molecular clouds, stripping electrons from atoms and shredding bonds that had taken millions of years to form. This wasn't just an obstacle for early chemistry, it was a full-scale reset, erasing much of the molecular progress made since the Big Bang and forcing the universe to rebuild from the ashes. The violence of this era is hard to overstate. Before reionization, the universe was filled with neutral hydrogen gas that absorbed ultraviolet light like a cosmic sponge, protecting deeper regions where molecules could thrive. But as population Roman 3 stars ignited, their intense radiation began ionizing this gas, creating expanding bubbles of transparency where UV light could travel freely. These weren't gentle transitions, they were frontiers of destruction, advancing at speeds approaching 1% of light speed. Within these bubbles, molecular hydrogen stood no chance. The same UV photons that helped create it initially by ionizing hydrogen atoms into reactive protons now became its executioners, breaking H2 apart faster than new molecules could form. Astronomers call this the photon underworld effect. Even as molecules formed in cooler pockets of gas, the constant barrage of radiation meant their lifespans were brutally short, some lasting mere decades before being torn apart. Computer simulations show entire molecular clouds evaporating like morning fog, their carefully assembled chemistry undone in cosmic instants. The numbers are staggering. During peak reionization, the universe may have lost up to 90% of its molecular hydrogen inventory. This wasn't just a setback, it fundamentally altered the timeline for cosmic evolution, delaying the formation of subsequent star generations until conditions stabilized. But here's the paradox: this destruction also seeded future complexity. The same UV radiation that wiped out molecules also created a soup of ionized particles, protons, electrons, and highly reactive atoms that would later enable more robust chemistry. When these charged particles eventually recombined in cooler regions, they did so with extra energy, catalyzing the formation of molecules that couldn't have existed in the quieter pre-reionization era. It's like burning a forest to enrich the soil. The immediate effect is devastation, but the long-term result is fertile ground for new growth. The evidence for this molecular wipeout is written in the cosmic microwave background's polarization patterns, which bear the scars of reionization timeline. Even more telling are the Lyman alpha forests, absorption lines in quasar spectra that reveal how suddenly and unevenly different regions of the universe were ionized. Some gas clouds show multiple layers of ionization and recombination, like tree rings recording cycles of cosmic fire and renewal. What emerges is a story of resilience. The molecules that survived did so by retreating into the deepest shadows, dense cores shielded by dust or the outer fringes of ionization fronts. These refuges became the nurseries where chemistry could regroup, eventually giving rise to the molecular diversity we see today. Reionization didn't just erase the universe's first chemical experiments, it stress-tested them, ensuring only the hardiest molecular pathways would shape our cosmic future. While the first stars shaped the universe with their light, another invisible force was at work: primordial black holes, lurking in the darkness and spewing radiation that rewrote the rules of chemistry. These cosmic behemoths, some as small as asteroids yet denser than neutron stars, could have been both destroyers and unlikely architects of the earliest molecules. Picture a black hole no bigger than a mountain, yet hotter than the sun's core, emitting a relentless barrage of X-rays and gamma rays as it devoured surrounding gas. In one breath, this radiation tore molecules apart. In the next, it supercharged the very reactions needed to build them back up. The paradox lies in the physics of accretion. As primordial black holes sucked in hydrogen and helium from nearby gas clouds, the infalling matter didn't just vanish, it spiraled into a glowing disk of plasma, heated to millions of degrees. This extreme environment became a particle accelerator, churning out high-energy photons that could blast electrons off atoms halfway across a galaxy. For fragile molecules like hydrogen or helium hydride, it was a death sentence. Any bond that formed near these radiation machines would be shattered almost instantly. Yet at the fringes of this chaos, something unexpected happened. The same radiation that destroyed molecules in the inner regions energized colder gas farther out, creating pockets where ionization actually boosted chemistry. Here's how: when X-rays ionized hydrogen atoms at the outskirts of a black hole's influence, they created a soup of free protons and electrons. These charged particles acted like molecular matchmakers, lowering the energy barriers for atoms to bond. Laboratory experiments simulating these conditions show molecular hydrogen forming 10 times faster in irradiated gas than in quiet regions. It's like nature's version of shock therapy, brutal but effective. Some models even suggest that black hole radiation could have synthesized complex molecules like water or carbon monoxide indirectly, by first breaking down their precursors and then reassembling them in cooler zones. The most tantalizing clue comes from quasars, ancient black holes billions of times the sun's mass, whose light reveals absorption lines from molecules in their surroundings. Despite the hostile environment, these quasars harbor molecular hydrogen, carbon monoxide, and even hydroxyl radicals. If supermassive black holes can sustain chemistry in their violent neighborhoods, perhaps their smaller, primordial cousins did the same in the early universe. Yet the story doesn't end there. Some theorists propose that black hole radiation didn't just assist chemistry, it directed it. The intense X-ray beams could have carved channels through gas clouds, creating temperature gradients that funneled atoms into specific regions. Over time, this might have established chemical hotspots where certain molecules dominated, effectively programming the universe's first periodic table. Imagine these black holes as cosmic DJs, remixing the primordial soup into new molecular configurations, some destined for destruction, others primed to become the building blocks of life. The legacy of this push and pull might still be visible today. In modern galaxies, black holes and star formation often exist in an uneasy balance. Too much radiation stifles molecule formation, while too little leaves gas too warm to collapse. This delicate dance could trace its origins to those first black holes, whose radiation set the tempo for cosmic chemistry. So while they were agents of chaos, they might also have been the unseen conductors of the universe's first molecular symphony. Carbon should have been one of the first complex elements to emerge in the early universe, yet for hundreds of millions of years, it was nearly absent from the cosmic stage. This missing carbon problem baffles scientists because carbon's unique properties make it the backbone of organic chemistry. Its scarcity early on wasn't just a quirk, it was a roadblock delaying the universe's chemical evolution. The culprit, a cosmic catch-22. Carbon forms inside stars through a process called the triple alpha reaction, where 3 helium nuclei fuse together. But here's the catch. This reaction requires temperatures over 100 million degrees and precise conditions that simply didn't exist until the first generation of stars matured. Before those stars ignited, the universe was stuck in a chemical deadlock. Hydrogen and helium dominated, with only trace lithium and beryllium as heavier elements, none of which could form stable, complex molecules. Carbon's absence meant no carbon monoxide, no methane, no formaldehyde, none of the molecular diversity we now associate with star-forming regions. This wasn't just a minor delay, it put the entire timeline of cosmic chemistry on hold. Without carbon's ability to form strong yet flexible bonds, the universe had to wait for stellar alchemy to catch up. Then came the game changer, asymptotic giant branch stars, the cosmic carbon factories. These aging stars, many times heavier than our Sun, developed layered interiors like cosmic onions. In their helium-rich shells, the triple alpha reaction finally kicked into gear, churning out carbon atoms that were then dredged up to the surface by powerful convection currents. When these stars eventually shed their outer layers, they sprayed this freshly minted carbon into space like celestial gardeners sowing the seeds of future chemistry. But carbon didn't spread evenly. Supernova explosions from massive stars distributed it in turbulent waves, creating patchwork regions where carbon-rich gas mingled with pristine hydrogen. This uneven distribution had profound consequences. In carbon-enhanced clouds, molecules like carbon monoxide formed readily, acting as efficient coolants that accelerated star formation. Meanwhile, carbon-poor regions remained chemically stagnant, stuck in an earlier phase of cosmic evolution. Modern astronomy reveals this divide in stunning detail. Spectroscopic studies of ancient gas clouds show wild variations in carbon abundance, with some regions containing 10,000 times more carbon than others. These carbon oases became hotspots for complex chemistry, while their impoverished counterparts languished. The implications are staggering. The universe didn't enrich itself uniformly, but in fits and starts, creating a mosaic of chemical potential that still influences galaxy formation today. The resolution of the missing carbon problem reveals a deeper truth about cosmic evolution. Sometimes, nature needs the right tools before it can build complexity. Carbon wasn't absent by accident. It was waiting for the universe's first stars to forge it. And once it arrived, it didn't just fill a gap. It transformed the cosmos from a monochrome landscape of simple gases into a vibrant chemical workshop where life's ingredients could finally take shape. Molecular hydrogen didn't just exist in the early universe, it shaped it. H's secret power lay in its ability to act as a cosmic air conditioner, radiating heat away from gas clouds and triggering a chain reaction that transformed the cosmos. Picture a vast, swirling mass of hydrogen gas, too warm and energetic to collapse under its own gravity. Without some way to shed that heat, it would have remained diffuse and lifeless forever. But when molecular hydrogen formed, everything changed. Unlike single hydrogen atoms, which can only cool by emitting ultraviolet light, a weak and inefficient process, H2 molecules vibrate and rotate when they collide, releasing energy as infrared radiation. This subtle shift turned them into natural radiators, bleeding heat from gas clouds with startling efficiency. The numbers are staggering. Simulations show that gas clouds rich in H2 could cool to temperatures just 30 degrees above absolute zero, 10 times colder than clouds of atomic hydrogen alone. That temperature drop was the difference between a cloud remaining a wispy haze and one dense enough to fracture into stellar nurseries. Think of it like a pot of boiling water versus a block of ice. The colder the material, the more easily gravity can pull it together. And once those first dense cores formed, they became gravitational anchors, drawing in more gas and accelerating the process exponentially. Some calculations suggest molecular hydrogen's cooling effect may have cut the time needed for the first stars to form by hundreds of millions of years. But H2 didn't work alone. Its cooling power was amplified by a cosmic feedback loop. As gas clouds contracted, their density increased, which in turn boosted the rate of molecular hydrogen formation. More molecules meant more cooling, which led to further contraction, a runaway process astrophysicists call cooling-induced collapse. This cycle created sharp temperature gradients within clouds, with frigid, molecule-rich cores surrounded by warmer envelopes of atomic gas. These cold cores became the birthplaces of not just stars, but the first protogalaxies, their growth supercharged by the relentless efficiency of H's infrared glow. The evidence for this molecular refrigeration is etched in the cosmos. Modern telescopes observe the same cooling mechanisms at work in nearby gas clouds, where pockets of H2 emit telltale infrared signatures as they prepare to form new stars. Even more compelling are observations of ancient galaxies at the edge of the observable universe. Their light, traveling for over 13 billion years, reveals spectral lines consistent with H2-driven cooling in their earliest phases. These distant time capsules show molecular hydrogen acting as the universe's original cold engine, quietly enabling the transition from formless gas to structured brilliance. Yet this cooling effect had an ironic twist. While H2 helped birth the first stars, those same stars ultimately became its greatest threat. As massive population Roman III stars ignited, their fierce ultraviolet radiation dissociated H2 molecules faster than they could reform, temporarily shutting down the cooling mechanism that created them. It's a paradox that echoes throughout cosmic history. The very processes that build complexity often contain the seeds of their own destruction. But without those first cold, molecule-rich clouds, the universe might never have lit up at all. So the next time you look up at the night sky, remember, every star you see owes its existence in part to the humble molecular hydrogen that first taught the cosmos how to chill. Water in the early universe sounds like a contradiction. A splash of liquid in a cosmos still too hot for rain. Yet some radical theories suggest water molecules might have existed mere hundreds of millions of years after the Big Bang, long before stars forged oxygen in significant quantities. This primordial water hypothesis challenges everything we thought we knew about cosmic chemistry's timeline. Imagine pockets of space just cool enough for stray oxygen atoms, forged in rare, violent collisions, to latch onto abundant hydrogen, forming H2O in the darkness. Not oceans or even ice, but solitary molecules drifting through voids, each one a microscopic rebel against the universe's fiery youth. The math behind this idea walks a razor's edge. In standard models, oxygen needed stellar furnaces to become abundant enough for water formation. But quantum chemistry offers loopholes. When ultraviolet radiation blasted apart carbon monoxide molecules in early gas clouds, it could have liberated trace oxygen atoms as a byproduct. These lone radicals would have been desperate to bond, and hydrogen was everywhere. Laboratory experiments show that at temperatures just above absolute zero, conditions present in the universe's coldest pockets, water molecules can form through reactions so unlikely they'd be dismissed as impossible elsewhere. Yet given enough time and space, even the rarest events become inevitable. The smoking gun might lie in ancient quasars. In 2020, astronomers analyzing light from a 13-billion-year-old quasar spotted an absorption line matching water's fingerprint. The kicker, this signal appeared in a galaxy barely 700 million years after the Big Bang, far too early for conventional star formation to have produced much oxygen. Critics argue it could be noise or a different molecule masquerading as water, but if confirmed, it suggests some oxygen escaped stellar production lines entirely, forming water through exotic pathways we're only beginning to imagine. What's wildest isn't that primordial water might have existed, it's where it could have ended up. These early molecules wouldn't have stayed free-floating for long. Charged water ions act like molecular Velcro, sticking to interstellar dust grains and building up microscopic ice layers one molecule at a time. Over eons, these icy coatings could have become the raw material for comets, transporting water across galaxies long before planets formed. That raises a staggering possibility. Some of the water in your glass right now might predate the sun itself, a relic from an era when the universe was still figuring out the recipe for wetness. The implications ripple outward. If water existed earlier than thought, it reshapes our understanding of cosmic chemistry's pacing. Complex molecules like alcohols or sugars need hydroxyl groups, oxygen-hydrogen units as building blocks. Primordial water could have jump-started organic chemistry billions of years earlier than current models allow, turning the universe into a prebiotic playground long before Earth existed. It's a reminder that nature's ingenuity often outstrips our theories, and that even the most fundamental substances might have histories far stranger than we've dared to dream. At the subatomic level, the vacuum of space isn't empty, it's a seething quantum foam, where spacetime itself churns with fleeting particles and antiparticles popping in and out of existence. These microscopic fluctuations might seem insignificant, but imagine their collective power in the early universe, where spacetime was denser and more volatile. Some theorists propose that these quantum tremors didn't just flicker passively, they actively catalyzed the formation of molecules too exotic or unstable to survive in today's cosmos. Picture spacetime itself as a molecular workshop, its brief but violent wrinkles offering the perfect pressure and energy for bonds that defy conventional chemistry. One tantalizing candidate, positronium hydride, a bizarre hybrid of matter and antimatter. Normally, when an electron meets its antimatter twin, a positron, they annihilate in a flash of gamma rays. But in the quantum foam's chaos, simulations suggest fleeting moments where a positron could bind with a hydrogen atom, creating a molecule that exists for mere nanoseconds before self-destructing. These ephemeral unions might sound like cosmic trivia, except they could have left fingerprints in the primordial plasma. Annihilation events from positronium hydride could have subtly altered the balance of photons and baryons, leaving traces in the cosmic microwave background we might still detect. Even wilder is the idea of chromium compounds, hypothetical molecules forged in pockets where quantum foam temporarily warped the flow of time itself. In these twisted spacetime bubbles, atomic nuclei might have experienced time at different rates than their electrons, creating distorted orbitals that allowed impossible bonds. Think of it like a chemical reaction where the ingredients are dancing to different beats, producing structures that collapse once time resyncs. While no direct evidence exists, some physicists argue that certain anomalies in the distribution of light elements, like lithium's puzzling scarcity, could hint at these transient quantum alchemies. The real mind-bender, quantum foam, might not just have enabled exotic molecules. It could have guided the universe's chemical evolution. Random fluctuations would have created a patchwork of conditions, some regions favoring hydrogen formation, others briefly hospitable to helium hydride or even carbon chains. Over time, this chaotic lottery could have nudged certain molecular pathways to dominance, essentially letting space-time vote on which chemistry would shape the cosmos. It's a radical twist on Darwinism, where the fittest molecules weren't just selected by environment, they were shaped by the quantum fabric of reality itself. Detecting these ghostly fingerprints won't be easy. Today's quantum foam is too faint to influence chemistry visibly, and any primordial exotic molecules vanished billions of years ago. But future gravitational wave detectors or precision measurements of the cosmic microwave background might uncover subtle imprints, anisotropies, or polarization patterns that betray spacetime's turbulent youth. Until then, this theory remains a thrilling what-if, reminding us that the universe's first chemistry might have been far stranger and more creative than we ever imagined. Neutrinos might be the universe's most elusive particles, ghostly travelers that slip through planets like they're not even there. But in the early cosmos, their sheer numbers could have tipped the scales of molecular chemistry in ways we're only beginning to understand. Picture a universe so dense with neutrinos that trillions pass through every cubic inch of space each second. While individually weak, this constant subatomic drizzle might have collectively nudged atoms into configurations that altered how and when molecules formed. The key lies in their subtle interactions. Neutrinos rarely collide with matter, but when they do, they transfer tiny amounts of energy like a cue ball barely grazing another in a game of pool. In today's sparse universe, these nudges are negligible, but in the first few minutes after the Big Bang, when neutrinos outnumbered protons by 1,000,000,000 to 1, their cumulative effect could have been profound. Simulations suggest neutrino kicks might have slightly heated hydrogen gas, delaying the cooling needed for molecular bonds to stabilize. That delay, measured in mere millions of years, could have reshaped the timeline of star formation, pushing back the universe's first light. Yet in some cases, neutrinos might have played the opposite role. When they scattered off electrons in primordial plasma, they created ripples in the cosmic fluid, tiny density variations that became the seeds for future gas clouds. These ripples didn't just influence where matter clustered, they also affected how it clustered. Regions with slightly higher neutrino interactions may have developed colder pockets where molecules formed earlier, creating a patchwork of chemical readiness across the cosmos. It's like tossing pebbles into a pond. The ripples seem small, but they change where every floating leaf eventually drifts. The most compelling evidence comes from fusion experiments here on Earth. When scientists study neutrino interactions in supercooled detectors, they've observed unexpected energy transfers that align with early universe models. These lab-born glimpses hint at a hidden dynamic. Neutrinos might have preferentially heated certain particle spins or electron energy states, subtly favoring the formation of specific molecular bonds over others. In a universe where every competitive edge mattered, this neutrino bias could have steered chemistry down paths we now take for granted. What's wild is that we might be seeing echoes of this today. The cosmic microwave background carries faint imprints of neutrino drag anisotropies that match predictions of how these particles smoothed out primordial density fluctuations. If neutrinos helped sculpt the distribution of early matter, they indirectly set the stage for where and when molecular clouds could thrive. So while they rarely get credit in cosmic chemistry, neutrinos might have been the universe's invisible choreographers, guiding atoms into their first delicate dances without ever leaving a visible footprint. Their influence was ghostly, but their legacy is written in every molecule that followed. Dark matter doesn't just hide in the shadows, it might have forged its own invisible chemistry. While we've spent decades searching for individual particles, some theorists propose an electrifying alternative. What if dark matter atoms bonded together, creating molecules we can't see? The idea sounds like science fiction, but the math reveals startling possibilities. Picture an exotic version of hydrogen where hypothetical dark protons and dark electrons orbit each other, forming structures eerily similar to ordinary matter, just completely undetectable. These shadow molecules wouldn't interact with light or conventional forces, yet their gravitational influence could have subtly sculpted the cosmos from behind the curtain. The theory hinges on dark matter's potential complexity. Most models assume it's simple, lonely particles drifting through space without much interaction. But nature rarely settles for simplicity. If dark matter experiences even a faint analog of electromagnetism, its particles could attract and repel, forming atoms and eventually molecules. Simulations show that in regions where dark matter clumped densely after the Big Bang, these interactions might have birthed sprawling dark molecular clouds, cosmic ghost towns where invisible chemistry unfolded parallel to our own. Unlike normal molecules, these wouldn't rely on electron bonds. Instead, they'd tether through unknown forces, creating architectures that defy our periodic table. Here's where it gets wild. Some versions of this theory suggest dark molecules could have acted as scaffolding for visible matter. As ordinary hydrogen and helium pooled in the gravity wells of dark molecular clouds, their collapse into stars and galaxies might have been guided by an unseen hand. Think of it like a theater performance where the actor's visible matter follows stage directions whispered by an invisible crew. This could explain baffling observations like why small galaxies pack more dark matter than expected, or why certain star clusters orbit in patterns that seem choreographed by hidden structures. Yet proving any of this remains a nightmare. Traditional telescopes can't see dark molecules, and particle colliders haven't spotted the hypothetical forces that would bind them. But there's a glimmer of hope. If dark molecules exist, their collective gravity should warp spacetime in distinct ways. Future gravitational wave detectors might catch these distortions, like hearing the faint hum of an invisible orchestra. Others propose hunting for rare, high-energy collisions where dark molecules briefly light up by interacting with ordinary particles in cosmic rays. The implications are staggering. If dark matter formed molecules, it didn't just passively fill the universe, it engineered it. Galaxies, stars, even life itself might owe their existence to chemistry we'll never directly observe. It's a humbling thought. The blueprint of reality could be written in bonds we can't see, by rules we're only beginning to guess. Carbon gets all the glory as life's essential element, but what if the universe flirted with silicon first? This isn't just sci-fi speculation. It's a serious challenge to carbon's chemical supremacy in the early cosmos. Picture a young universe where temperatures and pressures favored silicon's unique properties over carbon's. While carbon forms the backbone of every known biological molecule today, silicon shares eerily similar bonding abilities, 4 available electrons ready to link up, creating chains and rings just like its cosmic rival. The difference: silicon's bonds are slightly weaker, its compounds bulkier, and its reactions slower under Earth-like conditions. But the early universe wasn't just Earth-like, it was a maelstrom of extremes where silicon could have shined. Deep in primordial molecular clouds, where temperatures soared and radiation blasted through gas, silicon had hidden advantages. Its larger atomic size made it less vulnerable to ionization by ultraviolet light, allowing silicon-hydrogen compounds like silane CH4 to persist where methane CH4 might have been torn apart. Laboratory experiments simulating early cosmic conditions reveal something startling. Under intense pressure and heat, silicon forms stable networks with oxygen, creating silicate scaffolds that could have acted as cosmic training wheels for more complex chemistry. Imagine microscopic grains of silicon compounds, not just dust, but intricate molecular frameworks floating through space, offering surfaces where simpler molecules could assemble and react long before carbon-rich environments existed. Here's where it gets radical. Some astrochemists propose that silicon's real edge wasn't in mimicking carbon's organic dance, but in pioneering an entirely different chemical pathway. While carbon excels at building the delicate, reactive molecules of life, silicon's forte might have been structural. In the searing environments near young stars or in the shockwaves of supernova, silicon could have forged heat-resistant minerals and crystalline matrices. These durable structures might have provided stable workbenches where fragile carbon compounds later found shelter, like a cosmic incubation chamber for organic chemistry. Observations of distant protoplanetary disks support this. Silicon carbide grains, a compound almost never found on Earth, are shockingly common around young stars, suggesting silicon played an active role in early material formation. Yet the plot thickens with a cosmic twist of fate. Despite silicon's early potential, carbon ultimately won the chemical arms race. The reason lies in stellar alchemy. When massive stars exploded, they spewed carbon into space like cosmic confetti, while much of silicon got locked up in solid dust grains or bonded tightly with oxygen. Carbon's lighter weight also made it more mobile, able to float freely in gas clouds and react readily, while silicon compounds tended to clump or settle. This divergence wasn't just chance, it was written into the fundamental physics of nucleosynthesis. Carbon forms readily in stellar cores, while silicon requires rarer, more violent conditions. Over time, the universe became carbon-rich by default, leaving silicon's early promise as a forgotten prologue to cosmic chemistry. But what if we've been looking for life's origins the wrong way? The discovery of complex silicon-oxygen polymers in meteorites hints that silicon didn't just fade away. It might have laid groundwork carbon later exploited. Some theorists even speculate about shadow biochemistries, worlds where silicon-based molecules evolved differently, perhaps in extreme environments like scorching exoplanets or deep within icy moons. While Earth's life chose carbon, the universe's first molecular experiments might have been far more diverse than we ever imagined. Silicon's story isn't one of failure. It's a reminder that cosmic chemistry had multiple blueprints, and only time decided which ones got built. Plasma is often called the fourth state of matter, a seething, ionized soup where atoms are ripped apart into free electrons and nuclei. It's the last place you'd expect molecules to survive, let alone form. But the early universe was a realm of extremes, and in the fleeting moments after the Big Bang, plasma wasn't just a barrier to chemistry, it might have been its unlikely midwife. Imagine a cosmic paradox, molecules assembling in the same violent inferno that should have obliterated them, their existence measured in fractions of a second before being torn apart again. This is the plasma phase hypothesis, a radical rethinking of when and how the universe's first bonds were forged. The key lies in plasma's chaotic density. In the first microseconds after creation, the universe wasn't just hot. It was crammed with particles colliding at energies we can barely replicate in today's particle accelerators. Under those conditions, even fleeting molecular bonds could flicker into existence through sheer brute force probability. Picture two hydrogen nuclei slammed together by a shock wave, their mutual electrostatic repulsion overwhelmed by the plasma's pressure. For an instant, they'd share electrons in a crude approximation of a molecule before the surrounding chaos ripped them apart. These weren't the stable unions we think of today. They were more like quantum mirages, appearing and vanishing faster than space-time itself could register. Laboratory experiments with quark-gluon plasma, a state of matter mimicking the early universe's densest phases, hint at how this might work. When heavy ions collide at near light speeds, detectors occasionally catch signatures of transient molecules lasting mere yoctosecond, that's a trillionth of a second. While these aren't true molecules in the traditional sense, they exhibit bonding-like behavior, suggesting that even in the most hostile environments, nature finds ways to flirt with structure. Here's where it gets stranger. Some theorists propose that these ephemeral plasma molecules didn't just form randomly, they could have acted as cosmic catalysts. Each brief bond would have redistributed energy in its immediate vicinity, creating microscopic pockets of slightly cooler plasma. Over time, these fluctuations might have seeded larger-scale structures, like invisible breadcrumbs guiding the universe toward stability. It's a bit like trying to build a sandcastle during a hurricane. Each grain that momentarily sticks influences where the next one lands until eventually, against all odds, a pattern emerges. The plasma phase hypothesis doesn't just rewrite the timeline of molecular formation. It challenges our very definition of chemistry. If bonds can exist even momentarily, in conditions where atoms aren't fully atoms and electrons aren't firmly anchored, then the universe's path to complexity might have begun far earlier and in far wilder environments than we ever imagined. And while these plasma-borne molecules left no direct traces, their ghostly influence could still echo in the large-scale structure of the cosmos, etched into the distribution of galaxies like faint handwriting on the fabric of reality. Magnetic fields might seem like a modern cosmic phenomenon, something that only matters near pulsars or swirling galaxies. But their roots stretch back to the universe's infancy, where whispers of magnetism could have orchestrated the first fragile molecular bonds. Imagine a time before stars, when space was threaded with invisible filaments of force, weak compared to today's standards but strong enough to nudge charged particles into alignment. These primordial magnetic fields didn't just exist passively. They may have been the unseen hands that shaped where and how molecules could form, turning chaos into order one atom at a time. The key lies in plasma's behavior. In the early universe's ionized soup, free electrons and protons spiraled along magnetic field lines like beads on a wire, their paths no longer random but directed. This subtle guidance altered everything. Where fields were strongest, particles congregated, creating dense patches ripe for molecular formation. Where fields were weak or tangled, atoms remained scattered, too disorganized to bond. It's like comparing a bustling city to open countryside, the same number of people, but vastly different chances for connections. Even a field 1 billion times weaker than Earth's could have been enough to tip the scales, channeling the raw ingredients of chemistry into the universe's first molecular assembly lines. But magnetism's influence didn't stop at organization. It also provided stability. Modern lab experiments show that magnetic fields can suppress chaotic plasma motions, calming the turbulence that tears molecules apart. In the early universe, this damping effect might have given fragile hydrogen or helium hydride bonds precious extra microseconds to strengthen before radiation shattered them. Over millions of years, that tiny advantage could have snowballed, allowing molecules to accumulate in magnetically shielded pockets while less fortunate regions stayed barren. The difference between a molecular desert and an oasis might have come down to which way the cosmic compass pointed. The most tantalizing evidence comes from cosmic relics. Astronomers studying the polarization of light from quasars, ancient beacons whose rays traverse billions of light years, have detected faint imprints consistent with primordial magnetic fields. These signals align eerily with regions where molecular hydrogen is unusually abundant, as if the fields left a lasting signature in the chemistry they helped create. Even more compelling are simulations of the early universe that include magnetic effects. they produce molecular distributions matching real observations far better than models that ignore magnetism entirely. Here's the twist: these first magnetic fields might not have been random. Quantum fluctuations in the early universe could have generated them, imprinting a faint but structured pattern on the cosmos during inflation. If so, magnetism wasn't just a side effect of cosmic evolution. It was baked into reality's blueprint from the first moments. That means the molecules we see today, from the water in comets to the carbon in our DNA, might owe their existence to invisible forces that guided their birth before time itself had fully settled into its rhythm. The implications stretch beyond chemistry. If magnetic fields aided molecule formation, they indirectly set the stage for star birth, galaxy assembly, and even the emergence of life. They're the hidden conductors of a symphony we're only beginning to hear, their opening notes played in a universe too young to have realized their future importance. So while we can't see these ancient fields directly, their legacy is written in every molecular bond that followed, a reminder that the universe's grandest structures often grow from the subtlest beginnings. Cosmic inflation, the universe's explosive growth in its first fractions of a second, is often framed as a period of pure chaos, stretching space-time faster than light could chase it. But what if, in that frenzy, fleeting molecular structures flickered into existence, defying the very laws we assume govern that era? The inflationary chemistry model dares to ask whether the universe's most violent expansion didn't just set the stage for later chemistry, it might have briefly pioneered it. Picture this: as space-time ballooned exponentially, regions of ultra-condensed energy fluctuated wildly, creating microscopic pockets where temperatures and pressures momentarily mimicked the cores of stars. In these transient zones, particles collided with such ferocity that protons, neutrons, and electrons could have briefly assembled into proto-molecules, structures too unstable to survive inflation's end, but real enough to leave ghostly imprints on the cosmos. The math behind this idea bends conventional wisdom. Normally, inflation's breakneck expansion would tear apart any incipient bonds before they could stabilize. Yet quantum field theory suggests a loophole. In certain high-energy regimes, particles can enter quasi-bound states where they behave as if they're bonded despite lacking stable configurations. It's like two climbers briefly grasping hands mid-fall. Their connection doesn't last, but it redirects their trajectories. Simulations of inflationary plasma show that these quasi-molecules, though ephemeral, could have altered how energy distributed itself across the newborn universe. Some models even suggest they acted as microscopic lenses, focusing inflationary energy into filaments that later seeded galaxy formation. The most tantalizing evidence lies in the cosmic microwave background's faint anomalies, subtle temperature variations that defy standard inflationary predictions. These irregularities align eerily with patterns expected if fleeting molecular interactions briefly warp the plasma's density. Imagine dipping a sponge into water. Even after you remove it, the liquid surface retains traces of where the sponge disrupted it. Similarly, inflation's hypothetical molecules might have left wrinkles in spacetime that persisted long after the particles themselves vanished. Critics argue that inflation's energy scales were too extreme for any meaningful chemistry. But counterintuitively, extreme conditions can sometimes enable bonding that's impossible under milder circumstances. In particle accelerators, ultra-relativistic collisions occasionally produce exotic composite particles that exist for nanoseconds, proof that bonding isn't limited to serene environments. If lab experiments can create transient unions at trillion-degree temperatures, why couldn't the early universe? The implications are staggering. If inflation birthed even transient molecules, it means the universe was experimenting with complexity before the first atoms stabilized. These phantom structures wouldn't have been molecular in the traditional sense, more like quantum echoes of chemistry to come. Yet their influence might have cascaded across cosmic history, subtly biasing where matter clustered and how galaxies formed. It's a reminder that the universe's creativity isn't bound by our definitions of what's possible, only by the endless permutations of physics itself. Chain-like molecules in the early universe sound like a cosmic anachronism, a jumble of complex chemistry in an era thought to be dominated by simple atoms and fleeting bonds. Yet a daring fringe of astrochemists argues that the primordial soup might have cooked up polymers far earlier than we've ever dared to imagine. Picture this in the turbulent wake of the Big Bang, amidst swirling hydrogen and helium carbon atoms. Those scarce could have stumbled into rare alignments, linking together like microscopic railroad tracks across the void. These wouldn't be the elaborate proteins or DNA of today, but perhaps rudimentary chains of hydrocarbons or cyanopolyenes, straightforward molecular threads weaving through the chaos. The debate hinges on three radical premises. First, that trace carbon atoms forged in the depths of population Roman III stars could have concentrated in localized pockets through sheer statistical flukes. Second, that the early universe's extreme conditions alternating between searing heat and near absolute zero might have acted like a cosmic heartbeat, pulsing molecules into alignment during brief cooling periods. And third, that quantum tunneling, which helped hydrogen molecules form, could have given carbon chains a similar boost, allowing bonds to snap into place even when conventional energy thresholds weren't met. Laboratory experiments add fuel to the fire. When scientists simulate early universe conditions with lasers and cryogenic chambers, they've observed carbon atoms linking into chains as short as 3 or 4 units, no fancy catalysts required. These protopolymers are fragile, true, but in the cold vacuum of space, without oxygen or microbes to break them down, they might have persisted for millennia. Even more intriguing are observations of distant quasars, whose light reveals absorption lines matching molecules like Hc3 and cyanocetylene, a 3-carbon chain in galaxies barely a billion years old. If such complexity existed that early, why couldn't it have started sooner? Critics counter with the sterility bottleneck. The harsh ultraviolet radiation flooding the early cosmos should have shredded any delicate chains faster than they could form. But here's the twist: some polymers are surprisingly UV-resistant. Polyenes carbon chains with alternating single and triple bonds actually absorb harmful radiation and re-emit it as harmless infrared, acting like molecular sunscreen. In the shadows of cosmic dust clouds or on the icy surfaces of asteroids, these chains could have thrived, hidden from the universe's wrath. The implications rewrite more than just chemistry's timeline. If polymers existed early, they might have served as templates, primitive scaffolds that guided the formation of more complex molecules when conditions improved. Think of them as cosmic breadcrumbs left behind by a universe experimenting with structure long before life entered the stage. It's a humbling reminder that nature's ingenuity often outpaces our assumptions, and that the simplest threads can sometimes weave the grandest tapestries. Quantum entanglement defies everything we know about distance and connection particles linked across light years, reacting instantly as if no space separates them. Now imagine harnessing that spooky action to forge molecular bonds that transcend physical proximity. This isn't science fiction, it's a radical theory gaining traction among quantum chemists. In the early universe, where particles were packed densely and interactions happened at breakneck speeds, entanglement might have briefly enabled molecules to form in ways that would be impossible today. Picture 2 hydrogen atoms separated by cosmic distances, their electrons entangled during the Big Bang's chaos. Even as they drifted apart, their quantum states remained intertwined, creating a phantom bond that allowed them to feel each other's presence and react as if they were side by side. The mechanics of this are mind-bending. Normally, molecular bonds rely on electrons occupying shared orbitals, a physical overlap of wave functions. But entangled particles share a single quantum state regardless of distance, meaning their electrons could effectively coordinate without ever occupying the same space. Simulations of ultra-dense early universe plasmas show fleeting moments where entangled pairs exhibited bonding-like behavior, their spins and energies synchronizing in ways that mimicked traditional chemistry. These weren't bonds in the classical sense, they were quantum handshakes, agreements written in the subatomic fine print of reality itself. What's wild is that these entanglement-driven connections could have sidestepped some of the early universe's harshest obstacles. In regions where radiation should have prevented stable molecules from forming, entangled pairs might have exploited their non-local link to share energy or stabilize each other against disruption. Think of it like two dancers separated by a crowded room, yet moving in perfect unison because they're listening to the same song, no physical contact needed. This could explain anomalies in the cosmic microwave background where certain energy signatures suggest molecular activity occurred earlier or in more hostile environments than classical models allow. But the real kicker, these bonds wouldn't have lasted. As the universe expanded and decoherence tore entangled pairs apart, their ghostly molecular affiliations would have dissolved, leaving behind no direct traces. Yet their influence might linger. Some theorists propose that entanglement-mediated bonding could have subtly altered the distribution of matter, creating density variations that later guided galaxy formation. It's a cosmic game of telephone, where whispers from the quantum realm echoed into the large-scale structure of the universe. Experimental proof remains elusive, but tantalizing hints exist. Modern quantum labs have created entanglement-assisted reactions, where chemically separate particles exhibit correlated behavior, and observations of distant quasars reveal absorption patterns that defy conventional chemistry. Spectral lines suggesting molecules interacted across improbable distances. While far from conclusive, these clues keep the door open to a universe where the first bonds weren't just physical. They were quantum conversations spanning the void, written in a language we're only beginning to decipher. What if the molecules we consider native to our universe aren't entirely our own? The multiverse contamination theory proposes a mind-bending possibility that some of the earliest particles in our cosmos weren't homegrown but refugees from other realities. Imagine the fabric of spacetime as a vast, porous membrane where quantum fluctuations occasionally tear microscopic holes, allowing matter, or even entire molecules, to slip through from parallel dimensions. These interlopers wouldn't just be exotic visitors. They could have fundamentally altered the chemical trajectory of our universe in ways we're only beginning to suspect. The theory hinges on the physics of cosmic inflation. During the universe's explosive expansion, quantum bubbles of spacetime may have pinched off into separate universes, each with its own physical laws. But at the boundaries where these bubbles brushed against ours, brief portals might have opened nanoscopic wormholes permitting the exchange of particles. Picture a cosmic game of musical chairs where subatomic particles from alternate realities occasionally landed in our newborn universe, bringing with them properties unlike anything native to our physics. These rogue molecules wouldn't have been obvious invaders. Their strangeness might have been subtle, slight variations in isotopic ratios or bonding energies that defied local expectations. Some theorists suggest helium hydride could hold clues. This fragile molecule, long considered our universe's first molecular bond, appears in unexpected abundances within ancient gas clouds. Certain isotopic variants like helium-3 hydride show bonding strengths that deviate slightly from standard quantum predictions. While measurement error could explain the anomaly, contamination from a universe where nuclear forces were marginally stronger offers a provocative alternative. Even wilder is the idea that dark matter itself might be partially composed of multiversal immigrants or particles that slipped through during these early breaches, forever foreign to our reality's laws. The smoking gun might lie in cosmic anomalies. In 2022, astronomers studying the absorption spectra of a 13-billion-year-old quasar detected a mysterious line matching no known terrestrial or astrophysical molecule. Some researchers argue it could be the fingerprint of a compound impossible under our universe's physics, perhaps a tetrahedral arrangement of protons stabilized by exotic nuclear forces from another reality. Skeptics dismiss it as instrumental noise, but if confirmed, it would suggest that the cosmic chemistry set was never entirely isolated. Critics counter that multiversal molecules violate the principle of locality, the idea that physical interactions can't exceed light speed. But quantum entanglement already proves particles can share states instantaneously across distances. If entanglement can bridge space, why not dimensions? Simulations of brane cosmology, where our universe exists as a membrane floating in higher dimensional space, show that particle tunneling between realities, while rare, isn't forbidden by fundamental physics. The odds are vanishingly small, but in a cosmos as vast as ours, even the most improbable events become inevitable given enough time and space. Perhaps the most profound implication isn't about the past but the future. If molecules crossed universes once, they might do so again. Advanced telescopes could someday spot chemical signatures in distant galaxies that defy all known physics, not because our models are wrong, but because those molecules weren't forged in our universe at all. It's a humbling thought. The building blocks of reality might carry passports from worlds we'll never see, their origins written in quantum fine print we're only beginning to decode. Time crystals sound like something ripped from science fiction, structures that repeat not in space, but in time, oscillating between states eternally without losing energy. In the bizarre physics of the early universe, these hypothetical constructs might have served as molecular metronomes, ticking through the chaos to imprint repeating chemical patterns onto the newborn cosmos. Picture a universe where molecules didn't just form randomly, but were guided by invisible clocks, rhythmic quantum fluctuations that orchestrated bonds into precise, self-renewing formations. This isn't just theoretical whimsy, it's a radical reimagining of how order emerged from primordial chaos. The mechanics hinge on symmetry breaking. Normally, crystals like diamonds or quartz have atoms arranged in repeating spatial lattices. Their symmetry is frozen in place. Time crystals, proposed by Nobel laureate Frank Wilczek in 2012, take this further. Their components oscillate between configurations periodically, like a dance that never winds down, even in perfect isolation. In the early universe's extreme conditions, where space-time itself was still settling into its current rules, these oscillations could have acted as cosmic looms, weaving hydrogen and helium into transient but predictable molecular arrangements. Think of it as a molecular assembly line where atoms fell into place not by chance, but by the beat of a quantum drum. What makes this hypothesis explosive is its implications for complexity. Time crystals wouldn't have just created molecules, they could have synchronized them. In lab experiments with trapped ions, scientists have observed time crystal-like behavior where particles flip between quantum states in unison, a phenomenon called discrete time translation symmetry breaking. Translated to the early cosmos, this synchronization might explain why certain molecular distributions, like the clumping of hydrogen gas into filaments, appear eerily regular across vast distances. It's as if the universe's first chemistry was choreographed, with time crystals conducting the ensemble. Critics argue that time crystals require conditions too fine-tuned for the volatile early universe. Yet recent simulations of quark-gluon plasma, a state mimicking the post-Big Bang environment, show fleeting time crystal phases emerging naturally from quantum turbulence. These digital experiments reveal patches where particle interactions lock in to rhythmic cycles, briefly creating order before dissolving back into chaos. If even a fraction of these patches survived inflation, their rhythmic influence could have cascaded through cosmic evolution, subtly biasing how matter clustered. The most tantalizing evidence lies in the cosmic microwave background. Certain anomalous temperature fluctuations, patterns too regular to be purely random, align suspiciously with predictions of how time crystal imprints would distort primordial plasma. While far from conclusive, these anomalies hint that the universe's first molecules might not have been solitary pioneers, but participants in a grander, rhythmic design, one where time itself was the architect. Here's the profound twist. If time crystals existed, they didn't just shape early chemistry, they stretched time's arrow. Their ceaseless oscillations, immune to entropy's decay, could have provided a temporal scaffold against the universe's rushing expansion, offering fleeting pockets where molecular bonds had extra ticks to stabilize. In this light, the first molecules weren't just accidents of cooling gas. They were echoes of a deeper symmetry, whispers of a universe learning to count its own heartbeat before stars or galaxies even existed. Consider this: what if the early universe's complexity was just an illusion, a cosmic sleight of hand where molecules behaved as if they existed in fewer dimensions than they truly did? The holographic principle, a radical idea borrowed from black hole physics, suggests that all the information in a volume of space could be encoded on its boundary, like a three-dimensional movie projected from a two-dimensional surface. Apply this to the dawn of chemistry, and you get a startling possibility. The first molecular interactions might have been simpler than they appeared, governed by rules from a lower-dimensional shadow reality. At the universe's birth, space-time itself was still crystallizing. Some theories propose that certain dimensions were compactified, curled up so tightly that particles effectively moved in a flattened reality. In this constrained environment, molecules wouldn't have needed to navigate the full complexity of three-dimensional space. Chemical bonds could have formed along simplified geometric lines, like stick figures connecting dots on a flat plane. This isn't just abstract math. Lab experiments with ultra-cold atoms trapped in optical lattices show that restricting particles to two dimensions alters bonding behavior dramatically. Hydrogen atoms, for example, form more stable pairs in 2D configurations because their electron clouds overlap more efficiently when confined. The implications ripple outward. If early molecules operated under lower dimensional rules, their formation rates and stability would have defied classical predictions. Reactions that should have been improbable in 3D space, like three hydrogen atoms converging into a transient H3 molecule, might have been commonplace in a holographically compressed environment. Even the cosmic microwave background holds potential clues. Certain anomalies in its polarization patterns align with simulations of lower-dimensional quantum fluctuations imprinting on the early universe's plasma. But here's where it gets wild. The holographic principle doesn't just simplify chemistry, it could explain why some molecules survived reionization's fury. In a 2D projected universe, radiation would have traveled differently, with fewer pathways to disrupt bonds. Imagine sunlight trying to burn a painting versus a sculpture. The flattened version has fewer angles to attack. This might account for puzzling observations of molecular hydrogen persisting in regions theoretically too hostile for its survival. Critics argue that any dimensional reduction would have been fleeting, erased by inflation's spacetime stretching violence. Yet string theory offers a counterpoint. Compactified dimensions might have unfurled unevenly, leaving pockets where chemistry retained its simplified rules longer than expected. Astronomers may have already glimpsed these relics, distant gas clouds with anomalously high ratios of linear molecules like carbon monoxide versus branched ones could be the cosmic equivalents of shadows on a cave wall, echoes of a time when the universe's chemistry ran on simpler blueprints. This isn't just about rewriting the past. If the holographic principle shaped early molecules, its legacy might linger in quantum chemistry today. The way electrons tunnel through barriers or entanglement correlates molecular vibrations could be faint echoes of a dimensionality we've since outgrown. The universe's first bonds might have been forged in a reality we can no longer see, but their fingerprints could be hiding in plain sight, etched into the very laws of chemistry we're still unraveling. For every particle of matter in our universe, physics says there should be an equal and opposite antiparticle, a perfect mirrored twin with opposite charge. This symmetry suggests the early cosmos should have been teeming with anti-hydrogen, anti-helium, and even anti-molecules like anti-H2, dancing through the primordial plasma alongside their ordinary counterparts. Yet today, antimatter is vanishingly rare, a cosmic ghost haunting particle colliders and medical PT scans, but nowhere else. Where did all the anti-molecules go, and why didn't they build anti-stars or anti-galaxies? This is the anti-molecule paradox, one of the most glaring mysteries in modern cosmology. The puzzle begins with the Big Bang's accounting. Matter and antimatter should have been created in equal amounts, their mutual annihilation leaving behind nothing but pure energy. That we exist at all means something broke this perfect symmetry. For every billion antiprotons, there were 1,000,000,001 protons. That tiny imbalance, just one part in a billion, is all that survived to build our material universe. But here's the twist. While we've measured this matter-antimatter asymmetry in quarks and leptons, nobody knows if it applied to the first molecules too. Did anti-helium hydride briefly form before meeting its doom? Could entire anti-molecular clouds have flickered into existence before vanishing? Laboratory experiments offer tantalizing clues. In 2016, physicists at CERN synthesized anti-hydrogen atoms and held them stable for nearly 17 minutes, proof that anti-molecules could theoretically persist if isolated from matter. More recently, researchers observed spectral lines from anti-hydrogen matching ordinary hydrogen's emission patterns, suggesting anti-chemistry follows the same quantum rules. If anti-H2 formed in the early universe, it would have radiated and cooled identically to regular molecular hydrogen, potentially creating anti-version of the first star-forming clouds. So why don't we see anti-galaxies today? The leading theory involves CP violation, subtle differences in how particles and antiparticles decay. During the electroweak epoch, just trillionths of a second after the Big Bang, certain quantum interactions may have favored matter production over antimatter, amplified by phase transitions in the cooling universe. Anti-molecules, if they formed at all, would have been sitting ducks surrounded by a growing sea of ordinary matter primed to annihilate them. Yet some theorists propose a wild alternative. Maybe antimatter didn't vanish completely. Dark matter's gravitational effects could be explained by mirror anti-galaxies made from a shadowy form of antimatter that doesn't annihilate with ordinary matter. Others speculate about antimatter asteroids lurking in our solar system, leftovers from an ancient asymmetry battle. While no direct evidence supports these ideas, they remind us how much we still don't understand about the universe's first chemical experiments, including the ghostly anti-molecules that might have once been their own cosmic architects. The answer may lie in future observations. Upcoming gamma-ray telescopes could hunt for the distinctive annihilation signatures of leftover anti-molecular clouds, while ultra-precise measurements of helium hydride's quantum structure might reveal whether its anti-mirror displayed even the faintest asymmetry. Either way, the anti-molecule paradox isn't just about missing antimatter, it's a stark reminder that the chemistry we take for granted might have hinged on quantum imperfections smaller than one part in a billion. The universe didn't choose matter over antimatter by accident, but through rules we're only beginning to decipher. What if the universe's first molecules weren't just passive building blocks, but participants in something far stranger, a rudimentary form of cosmic awareness? This isn't mysticism, it's the edge of theoretical physics and panpsychist philosophy colliding. The consciousness-chemistry connection proposes that molecular bonds in the early universe did more than link atoms. They created networks of information exchange so complex they flirted with the barest glimmers of proto-consciousness. Picture hydrogen molecules not as inert structures, but as nodes in a vast, pulsating web where quantum interactions generated fleeting moments of coordinated behavior. Patterns that, under the right conditions, could resemble the most primitive precursors to awareness. At the heart of this idea lies integrated information theory, a framework suggesting consciousness arises when systems achieve a critical threshold of interconnectedness. Apply this to primordial molecular clouds and startling possibilities emerge. When hydrogen formed its first delicate bonds, those molecules didn't just exist in isolation, they vibrated, rotated, and exchanged energy in sync with their environment. In dense regions, their quantum states could have become entangled, creating transient molecular mines where information flowed across light years of gas. Think of it like a cosmic murmuration, individual starlings following simple rules, but together creating patterns that seem almost intelligent. The evidence is circumstantial but provocative. Modern lab experiments with Bose-Einstein condensates ultra-cold atomic clouds show that under extreme conditions, particles can exhibit coordinated behaviors resembling decision-making. When chilled near absolute zero, these atoms enter a unified quantum state, acting as a single superparticle. Scale this up to the early universe's molecular clouds, where temperatures were similarly frigid, and you have an environment ripe for macroscopic quantum phenomena. Some theorists argue that the same quantum coherence enabling superconductivity today might have, on a cosmic scale, allowed molecular networks to process environmental inputs in ways that blurred the line between chemistry and computation. But here's where it gets controversial. ORCH, or theory, championed by physicist Sir Roger Penrose, proposes that consciousness arises from quantum vibrations in microtubules within brain cells. Extend this to cosmology and you get a wild corollary. If microtubules can harness quantum effects for awareness, why couldn't molecular clouds? In this view, the universe wasn't just prepping for life, it was experimenting with raw experience itself, testing configurations where information integration briefly sparked flickers of something resembling sensation. Skeptics rightfully counter that ascribing proto-consciousness to molecules risks veering into anthropomorphism. Yet cutting-edge work in quantum biology shows that even terrestrial organisms exploit molecular-scale quantum effects, like photosynthesis near perfect energy transfer or birds' magnetoception. If life today harnesses quantum weirdness, why couldn't the early universe have stumbled upon similar tricks? The distinction may lie in duration. Where human consciousness persists, molecular awareness would have been ephemeral, vanishing as quickly as the quantum decoherence tearing apart delicate entanglements. The implications rewrite our place in cosmic history. If the first molecules danced with primitive awareness, then consciousness isn't a rare fluke. It's a latent property of matter, waiting for complexity to unlock it. This shifts the search for extraterrestrial intelligence from scanning radio waves to examining ancient gas clouds for quantum signatures that might betray their long-vanished sentience. It also raises eerie questions. Could the universe in its youth have dreamed in ways we can scarcely imagine? The answer, like those first fragile bonds, remains tantalizingly just out of reach. From the fragile bonds of hydrogen in the cosmic dark to the exotic possibilities of quantum entangled molecules and multiversal chemistry, we've journeyed through a universe far stranger than we often imagine. Each theory, whether mainstream or wildly speculative, paints a unique stroke on the canvas of cosmic origins. The simplicity of helium hydride's fleeting existence, the catalytic chaos of primordial black holes, even the radical notion of dark matter's invisible chemistry, all these ideas don't compete so much as they intertwine, revealing layers of a story still being written. What's breathtaking isn't just the diversity of these theories, but how they collectively reshape our understanding of beginnings. The early universe wasn't a static laboratory with one set of rules. It was a dynamic arena where quantum quirks, gravitational tides, and sheer chance collaborated to forge the first molecules. Some theories ground us in observable physics, like hydrogen's cooling power or deuterium's cosmic fingerprints. Others, like time crystals or holographic chemistry, stretch the limits of imagination, reminding us that reality often outpaces our assumptions. Here's the beautiful paradox: the more we learn, the more questions arise. Did silicon's early potential leave echoes in modern astrochemistry? Could antimatter have formed its own shadow molecules before vanishing? The answers aren't just about filling textbooks, they're clues to why our universe looks and behaves the way it does. Every molecule in your body, every star in the sky, traces back to these primordial experiments. So now it's your turn. Which theory resonates most? Do you see the universe's first bonds as a triumph of quantum persistence? Or do you favor the wildcard roles of dark matter or plasma phases? Maybe you've got a radical idea we haven't even touched. Drop your thoughts below. This conversation isn't just about the past. It's about how we, as curious beings, piece together the grandest story of all. After all, the universe didn't stop innovating after those first molecules formed. It's still evolving, and so is our understanding of where it all began.